Hey guys, so in this video I'm going to be showing a quick simulation of the 1D heat equation, which is one of the fundamental partial differential equations in math, physics, and engineering. I'll walk through the code, explain the math behind it, then show how the solution evolves over time. This would all be done in Python and using a simple numerical method. So first of all, what is the heat equation? The 1D heat equation is the derivative of u in terms of T times alpha times the second derivative of u in terms of x. So here the function of u would be the temperature at position x and at time t, while alpha would be the constant that controls how fast heat diffuses. The idea is if you start with a temperature distribution, heat would naturally move from hotter regions to cooler regions. This equation models exactly how the process would look mathematically. In this demo, I'm simulating a heat diffusion with a metal rod of length n. I'll start with a temperature that's shaped like a sine wave, meaning that the hottest point will be in the middle while the coolest points will be on the edges. And then I'll let the heat equation run forward in time using a numerical method called finite differences, which is essentially the approximation of the second derivative using the neighbors that are near it. So let's start going into the code. So these are going to be the necessary libraries you need. NumPy would be used for numerical manipulation. Matplotlib is for plotting things. This will be helping us with the animation, and then this will help us display the actual animation as I am using Google Colab and I cannot run this. So we run that, then we're going to need to set our constraints. So repeat that. And Nx will be the number of spatial grid points. Alpha, which is our heat diffusion, would be 0.1 dt. Alpha. And then the numbers time steps we're going to be using to simulate it, we'll say is 2000. So now I'll create a grid of x values and also set the initial condition. So in space 0, L, L, X. Then we will set the initial condition, which would be and then we'll also set unum equals u dot copy. There, boom, just like that. So now we want to plot our setup just to see what we're starting with, and for that we will be using the matplotlib. X equals plot.subplots, and then we'll set the x limit to 0 and L, and then the y limit will be that. And now we will set our titles. So we can just set the x label to x, y label to u, yep. And then we will set the title as 1D heat equation. And I messed something up. Oh, yep. I forgot to actually define it. Just like that. So as we see right here, it starts off as a wave where basically the middle is where all the heat is while the edges have 0. Next, we want to go to the heart of the simulation, the update rule, which is basically what finite differences is. So for that, we will use a function called update. plus alpha. This part is wrong. We want to do times of I plus 1 minus 2u of I plus u minus 1. Okay, now we want to set we would like to set the boundary conditions, which would be is equal to 0, and then u, the last value would also be equal to 0, so we'll set that to 0. Yep. And then we want to swap these references, so you would and then u, just like that. And we want to update the plotted lines, so line dot set underscore y data would be u. Oops, let me fix that. And then x dot set title. We can call it heat equation T equals, and then we'll go frame times dt, and this will basically give us the seconds, and then at the end we would like to return that. Okay, so that's the method we're going to be using. So now to actually make the simulation, this is basically the finite difference approximation of the second derivative u in terms of x. So every point gets updated based on its two closest neighbors, and that's kind of exactly how heat spreads from each point to their next closest points. So now we're going to use matplotlib's animation function to visualize the solution. So we're going to be using func. Yep, just like that. And then we'll use fig update. We'll call 600 frames, 20 intervals. Oops. Then cache frame data is equal to false. And now, because I'm using Google Colab, I need to display the animation as a HTML video. HTML, then it would be anim dot to HTML5 video, just like that. So now when we run this, it'll take a good amount of time to load, but the animation calls the update function hundreds of times, and each time it redraws the temperature profile. As the animation plays, you'll see the waves start to slowly flatten out, and it'll eventually become a constant value. This behavior exactly matches what we should expect mathematically, as the solutions of the heat equation tend to average out and lose structure over time. High frequency features fade away first, while low frequency components last longer. The heat equation shows up in things like heat conduction, diffusion of chemicals, smoothing in computer graphics, Gaussian blur, probability in random walks, and even in financial models. So we can see how it's slowly going down while the edges are getting higher. Thanks for watching this quick PDE visualization. You can do more with things like Fourier series and the wave equation. And PDEs are very vital for everything from learning math to going into physics to helping us in engineering. Thank you.